The year was 1970. America was still obsessed with horsepower. Big numbers, bigger promises, louder exhaust notes, wider tires. This was the era when dealerships felt like battlegrounds, when teenagers memorized displacement figures the way their parents memorized baseball stats, when every stoplight was an invitation, and Chevy thought it had the perfect answer: 400 cubic inches in a small block. On paper, it sounded insane. In showrooms, it sounded unstoppable. Magazine ads practically screamed it. The biggest small block ever built. More torque than you could use. All the muscle, none of the weight penalty. But in real garages, it became a nightmare. Because what most people don't realize is this: Chevy's 400 small block wasn't just hard to maintain, it was fighting itself from the inside, and once you understand why, you'll never look at this engine the same way again. You think you know small block Chevys. The 350, the 327, the legendary 283, bulletproof, cheap, easy to work on. Engines that would run forever on bad gas and worse oil changes. Engines that survived neglect like it was a badge of honor. Your uncle probably had one. Your neighbor definitely did. Half the trucks in America seem to run on some version of that architecture. So when Chevrolet announced the biggest small block ever built, people expected more of the same. Same reliability, same easy parts availability, same forgiving nature. They didn't get it, not even close. To understand how this engine went so wrong, you have to rewind to the late 1960s. The muscle car wars were peaking. Every manufacturer was locked in an arms race measured in cubic inches and quarter-mile times. Ford had big block torque with the 428 Cobra jet. Chrysler had the legendary Hemi, the engine that seemed to win everything it touched. Mopar's 440 was making waves, and GM had a problem. Big blocks were heavy, expensive to manufacture, thirsty at the pump. They required beefier suspension, bigger brakes, more robust transmissions. The cost added up fast. Small blocks, on the other hand, were lighter, cheaper, and easier to mass produce. The tooling was already paid for. The assembly lines were dialed in. What if Chevy could get big block torque from a small block package? What if they could give customers that low-end grunt, that effortless acceleration, without the weight penalty, without the sticker shock? That idea became the 400 cubic inch small block. Same external dimensions as a 350, same basic architecture, same engine mounts, same bell housing pattern. On the surface, it looked like just another member of the family. But inside, everything was pushed to the edge. And that's where the trouble started. The 400 small block debuted for the 1970 model year. It used a massive 4.1125-inch bore paired with a 3.75-inch stroke. Those numbers might not mean much if you're not an engine builder, but trust me, they meant everything. That stroke number should sound familiar because it's the same stroke Chevy would later use on the famous 383 stroker. But here's the critical difference. The 383 uses a smaller bore. It starts with the 350 block, which has room to breathe. The 400 didn't have that luxury. Chevy wanted displacement, maximum displacement, marketing displacement. So they bored the cylinders out as far as the casting would physically allow. We're talking razor-thin cylinder walls in some areas. There was no room left, no margin, no forgiveness, no safety buffer. Engineers knew they were walking a tightrope. Internal documents from the era show concerns about the design, but the pressure was on. The competition wasn't waiting. Customers wanted more, so Chevy pushed forward. And when you push cast iron that far, things get ugly. Right away, engineers ran into a cooling problem, a serious one. With those giant bores packed so tightly together, there simply wasn't space between the cylinders for traditional coolant passages. The water jackets that normally circulated coolant around the cylinder walls, they were squeezed out of existence. So Chevy did something unusual. They deleted them. The cylinders became what engineers call Siamesed, meaning the cylinder walls actually touched each other in the casting. No coolant flowed between them, no water jacket separated them, they shared material directly. To compensate for this, Chevy drilled tiny steam holes in the block and cylinder heads. These holes allowed trapped steam pockets to escape, preventing hot spots that could crack the block or blow head gaskets. It was clever engineering, really, a solution to an impossible problem. On paper, it worked. In real life, it created confusion, mistakes, and endless maintenance headaches. Because those steam holes had to line up perfectly between the block and the heads, every single one of them. Use the wrong head gasket, and you blocked them. Swap on heads from a 350 without drilling matching holes, and suddenly the engine ran hot. Very hot. The steam had nowhere to go. Pressure built up, temperatures spiked, and most mechanics didn't even know to look for this. The steam holes weren't something the average shop had dealt with before. They weren't in the basic rebuild manuals. They weren't common knowledge. So engines came back from rebuilds running worse than before. Overheating problems that seemed impossible to solve. And overheating was only the beginning. Early versions of the 400 used a 2-bolt main block. Now, you might think Chevy wanted to cheap out, save a few pennies per unit. But that wasn't it. The truth was worse. There simply wasn't enough material left for 4-bolt mains without weakening the block even more. Think about that. The casting was so thin, so pushed to its limits, that adding 2 more bolts per main cap would have compromised structural integrity. So Chevy accepted the 2-bolt design and moved on. But the consequences were real. The crankshaft was longer than a 350 crank. Heavier, under more stress with every combustion event, and the block flexed under load, not dramatically, not enough to see, but enough to matter. At high RPM, things started to move. Main caps shifted microscopically, bearings wore faster than they should, oil clearances changed, oil pressure dropped. Crankshafts didn't just fail. They suffered, slowly, quietly, until they didn't. One Chevy engineer later admitted in an interview that the 400 was never designed to rev like other small blocks. It wasn't meant to scream to 7,000 RPM. The red line was lower by design. Power came from torque, not RPM, from displacement, not speed. Factory ratings reflected this philosophy. Around 265 horsepower in early high-compression versions, modest by muscle car standards, but torque numbers pushed past 400 lb-ft in some applications. That was the selling point. That was what made the ads work. That torque felt incredible off the line, but it punished everything connected to it. Transmissions failed. The TH350 automatic, tough as it was, struggled behind the 400's grunt. Motor mounts twisted and cracked. Exhaust manifold bolts backed out from the constant vibration. Drive shafts needed more attention. U-joints wore faster. And internally, the engine demanded the kind of attention most owners weren't prepared to give. The oiling system was another sore spot. Like other small blocks, oil was routed up through the lifter galleries before feeding the crankshaft main bearings. This design prioritized the valve train. In most applications, it worked fine. But the 400 wasn't most applications. At high load, under hard acceleration, the top end could steal oil pressure from the mains. The heavy rotating assembly was starving for lubrication, while the rocker arms got more than they needed. In a smaller engine with a lighter crank, this wasn't catastrophic. In a 400 with heavy rotating mass and already stressed bearings, it was deadly. Mechanics started seeing the evidence. Spun bearings, scored crank journals that looked like someone had taken sandpaper to them, metal glitter floating in the oil pan, engines that had been rebuilt just 20,000 miles ago, already worn beyond safe tolerances, and nobody could figure out why at first. Then there was the harmonic balancer. Because of the 400's unique internal balance, or rather, its external balance, it required a specific harmonic damper and flex plate. The crankshaft wasn't balanced on its own like a 350 crank. It needed those external components to counteract vibration. Swap in the wrong parts, and vibration would slowly destroy the engine from the inside. The crank would wobble. Bearings would suffer. timing would fluctuate. It was death by 1,000 vibrations. Many owners didn't even know this. They'd rebuild the engine like a normal small block. They'd grab a balancer off the parts store shelf, bolt on a universal flex plate, and wonder why the engine shook itself to death within a year. The 400 wasn't forgiving of ignorance. You can probably guess what happened next. The 400 earned a reputation, not as a monster, but as a problem. Word spread through garages and car clubs. Mechanics started groaning when a 400 rolled in. Parts guys asked twice before ordering. The enthusiast magazines that had praised the engine in 1970 started publishing troubleshooting guides by 1973. By the mid-1970s, things got worse. Much worse. Emissions regulations tightened every year. Compression ratios dropped to meet the new standards. The early 10.25.1 engines were gone, replaced by smog-era versions running 8.5.1 or even lower, barely cracking 170 horsepower in some applications. Same displacement, less power, same maintenance issues. Now owners had all the drawbacks, with none of the glory. The engine that was supposed to deliver big block torque was delivering small block power with big block headaches. Cooling problems became legendary. Radiators that worked fine with a 350 suddenly couldn't keep a 400 alive on a hot summer day. The Siamese bores trapped heat with nowhere to send it. Steam holes clogged with rust and scale over time. Nobody knew to clean them. Nobody knew they were even there. Overheating warped heads. Cracked blocks. Blown head gaskets became routine. Some owners went through multiple engines. Some just gave up and swapped in 350s. And rebuilding one wasn't cheap or easy, because that thin cylinder wall design meant you couldn't overbore much. Maybe 0.0020 inches if you were lucky and the casting was good. Go 0.0030 and you were gambling. The machine shop had to sonic test the block first, checking wall thickness with ultrasound before cutting anything. Many blocks were junk before the rebuild even started. Walls too thin. Cores shifted from the factory. Hidden cracks that didn't show until the machine work revealed them. This wasn't a cheap $300 rebuild. This was expensive, specialized, risky. Then there were the heads. Factory 400 heads had those steam holes drilled from the factory. They came ready to work with the block. But later aftermarket heads often didn't. So builders had to carefully drill matching holes at precise angles in exact locations or risk disaster. Miss the angle and you hit water jackets. Drill too deep and you weaken the deck surface. Too shallow and the steam holes don't function. It required experience, patience, the right equipment. This wasn't backyard-friendly stuff. Even the cooling system required special care. Correct head gaskets with the right hole patterns, proper thermostat flow rates, no shortcuts, no cheap parts, skip one detail, and the engine punished you. And yet, there was something intoxicating about it. All that torque, right off idle. Before the tachometer even moved, the 400 was pulling. In trucks, full-size sedans, and even muscle cars, it delivered thrust without effort. It felt big. It felt lazy in the best way. You didn't need RPM. You didn't need to wind it out. You just leaned on the throttle and it moved. That feeling was addictive. Hot rodders noticed. By the 1980s and 90s, long after production ended, the 400 found new life as the foundation for the 383 stroker. Builders realized that if you fixed the weaknesses, improved oiling with priority main modifications, better cooling with proper head gaskets and steam hole work, quality machine work on the block and crank, it could handle serious power. The displacement was there. The potential was there. It just needed money, time, expertise. The average owner back in the 1970s didn't have that. They had a warranty card and a prayer. So Chevy quietly walked away. Production ended in 1980. No fanfare, no tribute, no special edition. The biggest small block ever built faded out as the emissions era took full control. The 350 survived because it was easier, more forgiving, less demanding. The 400 didn't. And here's the irony. Today, a properly built 400-based engine is a beast. With modern parts, forged internals, improved oiling mods, roller camshafts, and aluminum heads with properly drilled steam holes, it can make 500 horsepower easily. Some builders push past 600. Torque numbers that embarrass modern engines twice its size. Reliability that the original designers could only dream of. The 400 block, when treated right, is one of the best foundations for a street stroker ever made. But back then, it was ahead of its time and trapped by it. The Chevy 400 small block wasn't bad because it was poorly designed. The engineers knew what they were doing. They made calculated compromises to achieve something that seemed impossible. It was bad because it was pushed too far, too fast, with 1960s casting technology and 1970s emissions rules choking it from both ends. It asked owners to be careful, precise, informed, and most people weren't. That's why it overheated. That's why it failed. That's why mechanics groaned when one rolled into the shop. A small block that thought it was a big block and paid the price. If you enjoyed this deep dive into one of Chevy's most misunderstood engines, let me know in the comments what engine nightmare you want next. There are plenty more stories like this. Engines that promised everything and delivered heartbreak. Designs that looked perfect on the drafting table and fell apart on the street. And make sure to subscribe, because the next story is even crazier.